So we are at the start of Unit 9, and Unit 9 is about stoichiometry. Now, stoichiometry sounds like a really scary word and maybe a really scary concept, and I don't want to say no, it's not. It's a little bit challenging at first, but it is by far the most foundational piece to all of chemistry. So last unit we learned about the concept of the mole, and we were able to perform molar calculations. We're now going to extend that concept of the mole in terms of what does that mean with chemical reactions. Okay, we know chemists go into the lab, they perform chemical reactions. They probably are going to be a little bit curious about how much product they should produce from a given amount of reactants. The molar concept can help us figure that out. So we'll get into that later, but we're going to start off small with this cute little lesson on percent yield and percent air that allows us to figure out how efficient our chemistry is when we get in the lab and perform a chemical reaction. So let's see. First of all, I saw the term yield. What is a yield? In chemistry, a yield is the amount of product that's produced in a chemical reaction. So as scientists, we like to look at our yield in a way to measure how efficient we are or how good of a scientist we were. Okay, there are actually two yield values that we're going to be considering in today's lesson. The first is the actual yield, and then the second one is the theoretical yield. Okay, so actual yield. I like to abbreviate things because you know me, I don't like a lot of letters. Actual yield I like to abbreviate as AY. So the actual yield is the measured amount of product that is obtained from a real life reaction. This is also known as the experimental value. So let's pretend I'm a scientist, I'm going into the lab, I'm going to do a reaction, and I measure my product at the end, like on the balance. I'm going to see what mass of product I was produced. Well, that's an actual yield. It's how much you actually produce in the real world, non-perfect lab environment. Which brings us to the theoretical yield, or TY. So that's the maximum possible amount of product produced from a reaction, not what you actually produced. So the amount of product is actually calculated using this concept of stoichiometry. Like I said, more on that later. But this is what is known to be the accepted value, okay? So the theoretical yield is how much you should produce in a perfect world with no mistakes. In other words, in theory. So we know that we are not perfect scientists. There are things like sources of error all the time when we do a lab. So our actual yield will be different than our theoretical yield. But our theoretical yield is how much I should produce in a chemical reaction. So what does that mean to me? So I can actually look at actual yield and theoretical yield and use those two values to calculate something called a percent yield. A percent yield tells you what percentage of the product you were actually able to produce in the lab. So percent yield tells you how accurate you were. So a high percent yield is good. So if I look at this equation, I have my actual yield on top. That is the amount of product that actually was produced in the lab when my ding-dong self was doing the experiment. Okay, I do not trust my ding-dong self to get everything perfect. So I'm going to take that actual yield and divide it by the theoretical yield, in theory, how much I should have gotten. And if I multiply those values by 100, I will get a percentage, okay? So the larger your actual yield is, probably the larger your percent yield is, which a high percent yield is good. It's going to tell you how good of a scientist you are or how accurate you are. So let's go and see if we can implement this process by doing some practice problems. So I have a couple of practice problems for you to do today. The first one, and once again, I like to always say percent yield is equal to AY over TY times 100. I like to abbreviate this percent yield equation because, oh my gosh, so many letters in that actual equation. Okay, example number 1. Sam used his stoichiometry to predict that when mixing hydrochloric acid and sodium hydroxide, he should have produced 2.5 grams of sodium chloride. In the lab, Sam's group dropped the evaporating dish, and then only measured 1.6 grams of salt. What was the percent yield? Okay, well, the question here is asking me to solve for percent yield. So I'm like, okay, well, if I got to solve for percent yield, what is the equation for percent yield? So you're going to write the equation. And no matter, you can write it abbreviated. AY over TY times 100, right? Okay, so I'm like, well, I gotta figure out what the AY is and what the TY is and put them in there. So they give me two numbers here. The first number they give me is this 2.5 grams, and then the second number they give me is 1.6 grams. Which is the actual yield and which is the theoretical yield? Well, the actual yield is how much you actually produced in the lab. The theoretical yield is how much you should have produced according to your stoichiometric calculations. They said he should have produced 2.5 grams. So I'm looking at this guy, I'm like, oh my gosh, y'all, that's my theoretical yield. In theory, that's what I did. But he dropped the evaporating dish, and how much did he actually produce? Yes, 1.6 grams. So we have our two values. We always write the equation. The next thing we're going to show is the substitution of these two numbers into this equation with units, please. Okay, so we're going to say my actual yield was 1.6 grams. So I'm going to write that number on the top. And then my theoretical yield was 2.5 grams. And so I'm going to write that number on the bottom. And we're doing this to multiply by 100. So I have my equation. I have my substitution with the units in there, please. And now I'm ready to grab my calculator and get the answer to see how good of a scientist Sam was. Okay, so I go 1.6 divided by 2.5. Yes? And then I multiply it by 100. So what does this answer mean to me? This is 64%. And so Sam's group was 64% accurate. Now, that's not super close to 100, but that's at least better than 50%. So we're going to write this. So our answer is 64. I always do for my percentages, I extend it to the hundredths place. There are no sig fig rounding things because this is not a quantitative value. It's a relative value when we do calculate percentages. But that's what you'll see me do. And then I have percent. Yes? So my answer is Sam's group. Their percent yield, or how good they were in their science experiment, was 64%. Okay, second example, it says Joe also used stoichiometry to determine that 2.5 grams of sodium chloride should have been produced. So, there's my theoretical yield for this next problem. But his lab group was careful in the lab. Oh, good for them. And they did not drop anything. And they produced 2.3 grams of sodium chloride. So here is what they actually produced. This is their actual yield. And we are solving for my percent yield. Once again, establish our equation. Percent yield is equal to actual yield over theoretical yield times 100. The values that I'm going to be plugging in is my actual yield, what they produced in the lab, 2.3 grams, and the theoretical yield, what they should have produced in the lab, according to calculations. So I've got my equation, I've got my substitution, and now I'm ready to blast out my answer. I get my calculator. I'm super excited about that. I have 2.3 divided by 2.5 times 100. 92% yield. Oh my gosh, that is so much better than Sam's group. 92.00%. Wow, that's pretty accurate. So looking at this, if I ask you which group was more accurate in the lab, you would be looking at the percent yields. And Joe's group was the more accurate one because they had the higher percent yield. So another way I can measure how efficient I was in the lab besides percent yield is by calculating something known as a percent error. They're kind of like the opposites of each other. In fact, they are the opposites of each other. So a percent error tells you what percentage of error you had in obtaining your product. A percent error tells you how inaccurate you were. So I don't want to be very inaccurate. So as a result, I would want a low percent error. So the equation for percent error, it looks a little bit scarier than the equation for percent yield. And I'll show you a quick, real fun, easy way to get around that if you need to solve for percent error here in a second. But let's practice using this equation. So I'm looking at this. It looks like percent error is equal to your theoretical yield, which is what you should produce, minus your actual yield, which is what you did produce, divided by your theoretical yield. Now, looking at this, these little bars on the outside of those equations, they are important. They mean something. Those are absolute value bars. Whenever you have absolute value bars in an equation, that just means whatever the value is on the inside there, be it positive or negative, you are going to take the positive version of it. So if I put this calculation in and I get a negative value in there, you cannot get a negative percent error. So that will just tell you to remind yourself that you're taking the positive version of that. Okay, so let's see if we can implement this equation into some fun practice problems on utilizing this equation for percent error. Woo! Okay, here we go. So I like to abbreviate my equations. So I would say percent error is equal to ty minus ay over ty, right? And I'm taking the absolute value of that times 100, and I'm off the page, and that is okay. All right, here we go. Sam used his stoichiometry to predict that when mixing hydrochloric acid and sodium hydroxide, he should have produced 2.5 grams of NaCl. Y'all, this is the exact same question as the example number 1 that we did for percent yield. You're like, oh my gosh, then why are we doing this again? Because we're going to practice using this equation and see what we get, maybe compare the two things. Okay, so we do know that this 2.5 grams is my theoretical yield. And we know that they dropped the evaporating dish, so we only produce 1.6 grams. So that's his actual yield. We are solving for percent error here utilizing this equation. So I'm going to establish the equation. I'm going to write down percent error is equal to theoretical yield minus actual yield over theoretical yield with the absolute value bars. Now I'm going to show the substitution of these units, right? So my theoretical yield was 2.5 grams. The grams are important. Minus 1.6 grams divided by 2.5 grams times 100 equals. Okay, so I grab my calculator, keeping in mind that the absolute value bars does not mean I have to do anything sneaky in my calculator to represent those, but you just need to know that if you get a negative answer, you're going to take the positive version of it. So I have 2.5 minus 1.6, and then I'm going to be dividing that by my 2.5 again, divided by 2.5 times 100. So I did not get a negative number. If I did, I would totally represent that as a positive value here. Wait, I think I did something wrong. I did 2.8. Oh my goodness. Sabaka, get it together. Okay, let's start over again. 2.5 minus the actual value of 1.6 divided by 2.5. There we go. Times 100. Okay, amazing. So this is my percent error. So I'm going to write this down. 36.00%. So what does that mean? That is how much error out of 100% error he had doing this lab. That is not great. Let's compare to see how that would be with Joe's group now. So same question as before. We know that Joe, they calculated that it should have been 2.5 grams. That's the theoretical yield. They produced in actuality 2.3 grams. We are solving for the percent error. So establishing my equation, right? We go percent error is equal to theoretical minus actual divided by theoretical times 100. So now I've got my theoretical yield. I got 2.5 grams minus my actual yield, which for Joe's group is 2.3 grams. Divided by 2.5 grams times 100. So let's see what we get here. So we are ready to go. I say 2.5 minus 2.3 divided by 2.5 times 100. I get 8. 8. Whoops, there's my zeros a little squirrely. 8%. Well, what does this mean? That means Joe's group was only 8% bad. Their percentage error is only 8%. So this is another way to look at it, this percent error thing. I can look at the differences in percent error and get an indication of who did a better job in creating the amount of product that you should have made. So I want us to look at this real quick. So looking here on this slide, it's comparing the percent yield value to the percent error value for each one of the scientist groups. Did y'all notice that Sam's group, the one who was a little bit less good in the lab, if you add the percent yield of 64 to his percent error as 36, that adds up to 100. And for Joe's group, who was the better scientist group, their percent yield of 92% and their percent error of 8%, if you add those up, you get to 100%. Okay, so this is what I mean when I say percent yield and percent error are opposites, where the first one tells you how good you were, and the second one tells you how bad you were. So those are going to be parts of a whole here, okay? And so because for me at least, that percent error equation looks a little bit gnarlier, and I'm like, I do not like that at all. I always like to keep this concept in mind that you can, if I give you the percent yield and ask for the percent error, you can just say 100 minus the percent yield to solve for the percent error, as long as you show that math calculation on your page. So that's our cute little lesson on percent yield and percent error. It's just two different ways to represent how efficient you are as a scientist, okay? And we're going to actually continue on with this concept when we get into stoichiometry, because I will have you do fun things like calculate your percent yield from a lab experiment according to the stoichiometry value that you should have gotten. So this is very exciting for us. Welcome to stoichiometry. I cannot wait to dive into the first lesson on Stoic next.